Hello, everybody. Section 6.5 is entitled Physical Applications. So it's really applications to the area of physics. And we are going to pick just two sub-areas of this section. And those are number one, mass or weight, and number two, work, W-O-R-K. That's a four-letter word, isn't it? Well, anyway, work is basically, force times the distance, but we are going to use that in the context of integration. So let's look at these two specific applications in physics of integration. All right, so let's get into section 6.5. Okay, so the first of the two applications in physics, the first one is mass. And just to extend this, I know mass is the correct definition, the correct thing about physics, right? The mass is that which does not change whether you're on planet Earth or planet Jupiter or on the moon. The weight, of course, changes, but many times when we use this application, the mass defined with the density function, we can always apply the same idea to define the weight of something. And that's even more of a common application in the real world situation. So let me just give you a little context of what's happening here. Imagine a rod, it goes from A to B, all right? So the distance or the length of this rod is B minus A. And we mentioned this before when we talked about what an integral is. All right, so for each X, we have this definition of the weight or let's say the density. All right, so, oh, by the way, this letter that looks like a P in the English alphabet is actually an alphabet letter in the Greek alphabet, and that stands for rho. Okay, so make sure you read this as rho and not P. Okay, so the rho of X, for some reason, they like to use the letter rho to define the density function. So the density of this rod at this point X. All right, so in other words, at this point X, the density of the function is often measured in kilograms per meters or something like that. Okay, that's the situation. I mean, that's a question mark because sometimes it just depends on what you have here, right? But let's say X is measured in meters, and so this is a big rod. Maybe it's like a pole, like a telephone pole or something. And each part of the pole or rod is made of different material, where the density at X is defined as rho of X, right? And so again, what you can do is in terms of defining this definite integral, you can slice this rod into small, tiny pieces. That's the idea of partitioning into small subintervals, and each part, each piece can be defined as the rho of xi star, where I star is some point in the ith subinterval. And then if you multiply this by delta I delta xi, which is the length of the subinterval, this is an approximate weight or the mass of this piece, right? And if you add each of these pieces or the masses of all the pieces, that would be approximated by rho of xi star times delta xi. Now, again, this is the length of the ith subinterval, and this is the density function evaluated at the xi star, which is the the representative point of the ith subinterval. Okay. And again, this is strikingly similar to the first time we defined the definite integral, right? And if you take the limit as n approaches infinity, or more precisely, as the biggest subinterval goes to 0, more precisely, we say the norm or the maximum length of the subintervals of the partition goes to 0. Basically, this becomes the integral from A to B of rho x dx. All right. So this turns out to be the mass. Okay. Once again, think of what the definite integral means. All right. So you can also imagine R of a rho of r as some sort of function evaluated or defined on this interval AB, and you are finding the area under the curve, which is exactly the same thing as this. Okay, so think of this as a as we defined what a definite integral is as an accumulation, or as the area under the curve, or as the mass of this entire thing. Okay, all right, so let's do an example. Let's think of a telephone pole or something that is standing up like this. Okay, and well, maybe yeah, let's just think of this as a stick that's standing out, right? And it's in inches, and let's say the rho of x is 3 over x minus plus 1, and height goes from 0 to let's say what I want to do 8. Okay, so it's an 8-inch tall stick where the height is x inches, right? The density, let's just call this a weight. Okay, so this is the weight function, and it's measured in this case pound per inch per inch. Okay, and so for instance, right at this 0, if you evaluate rho at 0, that's 3, and so that's 3 pounds per inch. And if you go way up high here at h is equal to 8, this is 3 over 9, and so that's 1/3 pound per inch. In other words, it gets lighter and lighter as you go up higher and higher elevation on this, right? So the total weight is simply the integral from 0 to 8 on 3 over x plus 1 and then dx, right? Nothing to it. Okay, you know how to integrate this. Oh, do you? You can do u is equal to x plus 1 if you like. You really don't have to do this. Du is dx. So the integral of 1 over x1 dx, this is simply the natural log of x plus 1 plus c. So it's really not all that difficult. This turns out to be the natural log of x plus 1. And of course, there's a 3 in front. You can't forget that. And then if you evaluate this from 0 to 8. Now, of course, you can make the u substitution, and you can make this into a 3 times log of u as u goes from, let's see, 1 to 9. That would be okay. But I am actually, this is such a simple integral. I am using x and not u when I substitute these numbers. All right, so this is going to be 3 times log of 9 minus log of, oh, oops, that's, yeah, that's fine. When you plug in 0, you get log of 1. And of course, this is 0, so the answer is 3 times log of 9, approximately equal to, by the way, this is equal to log of 9 to the 3rd power, if you are interested in that. But anyway, the answer turns out to be 6.59 pounds approximately. So you can say this whole thing is 7 pounds, where the density function, which stands for weight per inch, changes from heavy here to light up here. But in other words, at every single point, the density function is different, right? The density function gets lighter and lighter, or less and less as you go higher and higher. But the way to add up ever-changing, varying quantity over 0 to 8 is exactly what we do with integration. So that's it, okay? All right, so that is the first example. The second application is work. Okay, now work, in short, is force times distance. So you may have learned this like in physical science class or something, right? So you say W is F times D, and that's fine if you're talking about something simple. Let's say you have this box and you're moving this, let's say 10 feet away, and the force is, let's say 5 pounds. Okay, so you're exerting the force horizontally at 5 pounds and constantly 5 pounds because of the friction. And by the way, if there is no friction, you just kind of push it with an infinitesimally small amount of work, and it's going to keep moving and moving forever, right? Of course, that doesn't happen in the real world because of friction. And let's say in order to keep moving this, you have to exert the force of 5 pounds for 10 feet, and the work is 50 foot-pound. Those are the units we use. Okay. Or if you have something you lift it vertically up, let's say you move this, what do I want to say? With a force of 10 pounds, and let's say this is 8 feet, of course, then the work is 80 foot-pound, right? So there's nothing to it. The reason I'm using this English or the British, I'm sorry, the American system, okay, like feet and pound, as opposed to the metric system is, well, a metric system, it gets a little complicated. How do you measure the force? You can use joule or, something that we are not very familiar with. You can do that. Distance, you can use meters. That's no problem. But then, sorry, the force, you use something like slugs, and then the work is going to be in terms of joules. So that's not as, we are not as familiar with that. So we are probably going to use, for our purposes, in this class, we'll use feet and pounds. And so the work is going to be described as or expressed as a foot-pound. Okay. Now, actually, see, when you move an object like this, if you exert force in this direction, it gets a little more complicated because your force may be pushed in or pulled in this direction, but because the object is moved in this direction, you only have to measure the horizontal component of this force, which requires a little bit of a vector calculus. So we will not consider that at this point. Probably in a later semester in your calculus, you will see something like that. Okay, but that's if all of these, both of these examples assume that your force is constant, right? So over here, you basically have this from 0 to 10, and at every single point you are exerting or you are pushing this or pulling this with a force of 5 pounds. So your integral is actually representing, see, I just multiplied this because that's what it says, if the force is constant. But it's actually what we are calculating is this definite integral, okay? In other words, 5 is the value assigned at every point between 0 and 10, and the consequence is that the work, which is the product of F and D, is just 50, right? Same thing here. Here, you go from 0 to 10, and you are using or applying the force of 8, this is from 0 to 8 with a force, a constant force of 10, that's a constant function of 10 dx, and of course that's 80. And so in this example, basically this is what we are calculating, the area under the constant function of 10 over this interval from 0 to 8. So what happens if F varies? Okay, in other words, if F of X is the force at X on an interval from A to B, so you have A and B, and force may change, maybe decreases here and increases here. Okay, well, as these pictures indicate, basically the work is simply the integral from A to B of Fx dx. Not hard, right? Okay, so that is another application of definite integral. Now, and a good example of this varying force would be a spring. Okay, let's say you have this spring and you are pulling it. Now, a scientist, a physicist by the name of Hooke, H-O-O-K-E, came up with this property, which is called Hooke's law, right? And you may be familiar with that. Basically, the force required to hold the spring at an equilibrium is going to be, or force being required to pull this to elongate the spring And this is the elongation X. Force required to pull the spring at elongation. Elongation is how much longer the spring is compared to when no force is applied to it. Elongation X is, this is equal to K times X. Basically, it says it's proportional to the elongation, right? So in other words, if you start at this point and if you start pulling it, and the further you pull, let's say you're pulling it at where X is, the elongation is 1 inch, then you are supposed to use a certain force, let's say 10 pounds. Then by the time you're pulling 2 inches, it's going to double. It's going to be 20 pounds, all right? And so this is proportional, directly proportional to K. So that varies, okay? In other words, the further you pull, the heavier it gets. So suppose, here's an example, okay? And this will be just the last example, the only example of a spring problem we will do in this section. Suppose 10 pounds is required to stretch a spring 2 inches. Okay, so what does it mean? Here, let's just assume this, all right? So you have this spring, and this is, where the elongation is equal to 0. And so you start pulling it, and when it's 2 inches, it requires 10 pounds, okay? So that's really the graph of the force required to pull the string at elongation X. And so, of course, when X is equal to 0, the force is 0. And so this is Y is equal to Kx. That's the force function. Let's just call this f of X. All right, according to Hooke's law, it is proportional to X. And so Fx is Kx. This is the basic formula for based on Hooke's law. Now, we don't know what K is. K is the spring constant. It depends on the spring itself, right? Some springs are harder to pull than others. And so K determines how difficult it is to pull that. But this relationship here to when X is equal to 2, Fx is 10. That tells you what K is, right? So find the force. Now, remember, this is force, not work. The force necessary to stretch this string 6 inches. And number 2, find the work. And I want you to clearly understand the difference between the force necessary to and the work done to stretch it 6 inches. All right, so remember I said you have this X and Y, or Fx, and from this relationship here, what we are told is this. Okay, so f of X is Kx, right? And we are given that 10 pounds is necessary to be holding this string or spring at 2 inches. So K, we don't know what K is, but it's 2. K is obviously 5. And this is the spring constant for this particular spring. Okay, in other words, it's 5 pounds per inch. That's what this is saying. So to pull it two, oops, let's just call this 2 here. 3, 4, 5, 6. Okay. And so to pull it 2 inches, it's required that you have the force of 10 pounds. Sorry, this is not inches, okay, in pounds. All right, so when the spring is at not stretched mode at rest, of course, you don't have to have any force, but if you're pulling it like 1 inch away then you would be holding it with 5 pounds, the force of 5 pounds, and so on. And so you have this thing here, right? Okay, so this line is, now we know f of x is 5x. And that's what you have to integrate. All right, so here's what's happening. Let's say you're pulling it from 0 to 1, right? Now, right when you are holding with the elongation of 1, you are exerting, or you are pulling it with 5 pounds. But before you get to that, by the time you get to it, you know, of course, you're holding it 5 pounds, but you start to slowly pull it, and here you have the 1 pound, 2 pounds, 3 pounds, 4 pounds, and 5 pounds. And by the time you stretch it 1 inch, right at this point, you're using the force of 5 pounds. But in order to go from 0 to 1, you have to add up all this area here. Okay, so that's the integral of this function from 0 to 1. And the same thing with this, and the same thing with this. In order to pull it so that the elongation reaches 6 inches, you have this force, this force, this force, this force. You have to add up all these forces. And so that becomes the work. The work is like the continuous addition of all the forces up until this point that you applied. So this is the integral from 0 to 6 of 5x dx. Hope you understand that, right? So 5x may be the force required at that moment when x is a particular value between 0 and 6. But the work has to do with the sum, continuous sum, i.e. the integral, the area under that force function. And so that turns out to be the work. Okay, just like, you know, back here, we calculated the area under the curve being the force. And so the force function, if it increases like this, you take the integral, that's 5 over 2x squared from 0 to 6. And for that, it's 5 over 2 of 36 minus 0, of course, right? And it's going to be 90. 90 what? Okay, it's not 90 pounds. Remember, right at this point, you're pulling it at, what is that? 30 pounds. But up until this, you have been pulling, and it gets harder and harder as the spring gets, you know, longer and longer. And so here you're pulling with a lot of force, but the accumulation of all the forces that were required to pull it up to this point where the elongation is 6, which means now the spring is 6 inches longer than it used to be. Okay, up from 0 to 6 inches, you have done the work, which is equivalent to 90, inch pound. In this case, not a foot pound, it's an inch pound, right? And so this is the amount of work done up until that point, right? So that's the difference between the force, which is momentarily or instantaneous, and work, which is the accumulation of the forces applied up until this point. All right, so there are many other applications mentioned in this section, but those are the only 2 we are going to do for our class. All right, and next up, we'll skip a couple of sections. Like in 6.6, we have moments and centers of mass, which you will probably learn in the 2nd semester of your calculus class. And so we'll go into 6.8 next.